Okay, so we will continue with whatever we had discussed about normal shock. So, I will start with this relation. We have derived this equation, which is the relation of Mach number with respect to the Mach number before the shock. So, we we have seen this okay. So, these are the two equations that we had seen last in the previous lecture. So, we were trying to see why mx less than 1 expansion shock are not possible physically. Even though the solution exists in this particular equation. Okay. So, this is not physically possible, but okay. So, one way of showing this is not physically possible is by calculating the entropy change. So, if I go back to my Gibbs equation, which is delta S, which is S1 S2 minus S1 or SX minus SY, is nothing but Cp ln Ty by Tx minus R ln Py by Px, okay, which is also equal to your Cp ln T0 y by T0 x minus R ln P0 y by P0 x, because that is entropy change that is connecting the two states. Okay. Or you can say entropy change between any 2 points, and then you have this point. Okay. Which we had seen to be if T0x equals T0y, we have seen P0y by P0x is e power minus delta S by R. Which we can write this in terms of Mach number and yeah. So, we have to so we will, before this we will have to show P0x, relation between P0x and P0y. Yeah, we will show that. Okay. So, so we will have P0 y by P0 x as e power minus delta s. Now, we will see how this can be represented in terms of Mach number. So, your P0 y by P0 x, I can write it as P0 y by Py into Py by Px into Px by P0x. So, this is an isentropic process. This is the stagnation state associated with y. So, that would be 1 plus gamma minus 1 by 2 my square to the power gamma by gamma minus 1. This is also the isentropic process that I would write it here, 1 plus gamma minus 1 by 2 mx square to the power gamma by gamma minus 1 into Px Py we know as 1 plus gamma by gamma mx square divided by 1 plus gamma my square. Okay. Now, this is my entropy change, e power minus delta s by r is this 1 plus gamma minus 1 by 2 my square divided by 1 plus gamma minus 1 by 2 mx square to the power gamma by gamma minus 1 plus gamma mx square divided by 1 plus gamma my square. Okay. So, you can show mx less than 1 not possible by two ways. One, taking this equation, said let us take this equation, or take this equation and show. Okay. So, let us take equation 1, which is Sx minus xy Cp ln Ty by Tx is we had shown the other day to be Tx by Ty is just 1 plus gamma minus 1 by my square divided by 1 plus gamma minus 1 by 2 mx square Ty by Tx. So, this would be x by y. Minus r ln Py by Px. Okay. Now, if mx is less than 1, let us see what happens. This is sy minus sx or simply delta x. Let us evaluate delta x and see the sign of delta x. So, if mx is less than 1 and implying we have seen my will be greater than 1 and your Py will be less than your Px. Okay. These two information you would get it from this relation mx. So, if mx is less than 1, you would get my to be greater than 1 and hence my Py would be less than Px. Okay. So, these two information we will use it here. So, if my mx is less than 1, my my is greater than 1 and Px is less than 1, which implies if I evaluate this, so my this term is less than this term. So, this would be less than 1. So, this ln of something less than 1 and here Py is less than your Px, but this comes with a negative sign. So, this again is a smaller quantity, which means your delta S would be negative, okay, which implies not a possible solution. You can also show that here. So, if my mx is larger, gamma is always greater than 1. This term is going to be mx is always going to be greater than 1, mx is less than 1, my greater than 1, and hence if you look at this terms, this term would be larger and this term would be larger, and since this is gamma minus gamma is greater than 1, gamma minus 1 is always less than 1. Okay. So, this quantity is always greater than 1. So, this would be a larger quantity, and then this is a smaller quantity, this is a smaller quantity. So, you need to find the magnitude of these two. So, between these two, mx square, this is going to be larger. Okay. So, you are going to have a small quantity here, which positive quantity here, which means your delta S would be negative, okay, implying your delta S is negative. Okay. For mx less than 1. For mx greater than 1, this equation still holds, and you can show that this is going to be a positive quantity. Okay. So, if I plot I will rub this. By R versus M, let us take the 0 line somewhere here and Mach number 1 somewhere here. This is my 1. If I plot this function, if I plot this function, okay, where I substitute my in terms of my mx. So, I can substitute this equation 1 here. Okay. So, what I do is I substitute my square as mx square plus 2 by gamma minus 1 by 2 gamma by gamma minus 1 mx square minus 1. Okay. So, this I substitute here and here, I would get e power minus delta S by R as a function of mx and gamma. Okay. So, if I substitute my my here, I would get this quantity e power minus delta S by R as a function of mx and gamma. So, now I plot mx versus e power delta S by R, I would get a curve something of this form. Okay. So, at mx equals 1, I will not have any change in my entropy for that particular jump which we had seen. For m1 greater than 1, I have entropy change positive. mx less than 1, I would have a negative entropy change. So, this is my negative entropy change, not possible for some fluids. Okay. It is still possible for some special case. possible in general fluids like air and other things, but if we use some other fluid, for example a case where you have an increase in pressure when you expand. So, when you expand, suppose you have a fluid, PV diagram, typical process we have is this is the expansion. So, I have a pressure that is reducing, my density decreases or the specific volume increases. That is our typical case of air or CO2 or whatever. Now, if you have a fluid which has a slope somewhere here, okay. So, when I expand, when I increase my volume, I have an increase in my pressure, okay. If I have a fluid like this, I can typically have a expansion shock, but again there the pressure is increasing. So, you have an increase in pressure even though the volume is coming down, okay. So, that kind of fluid can still have this kind of thing, but for the general purpose and for general fluids that we encounter, let us assume that the m less than 1, if mx is less than 1 there is no shock possible, only if mx greater than 1 there is shock possible. You show that using your entropy change starting from Gibbs relation and get it this particular variation. This is for a given gamma. So, let us say gamma equals 1.4 or so. Okay. For other gamma you will have a different, slightly different curve. Okay. Now, if we have decided that this is true, the subsonic shocks are not possible. Now, we can go ahead and draw the variation of mx and my. Mx and my. So, let us take something like this. Okay. So, this is my so called expansion wave, expansion shock. This is my compression shock. Okay, this would be slightly more it would be a steeper curve. Okay, this is delta S positive, this is delta S negative. Hence, we are not going to discuss this particular case where m is less than 1. So, subsonic expansion shocks we are not going to discuss, we are going to consider only this compression shock. So, if I redraw that curve, okay, if I start my coordinates from 1, I have mx, my. So, this is 1 0. So, I start my x axis from 1. So, my m equals 1 here and m equals 1 here. So, I would have a curve that is going like this. So, for every supersonic m, I would have a subsonic my. Okay. Okay, this is strictly for normal shocks. Okay. So, again you can look at the, so for the gas tables you can relate for every Mach number, supersonic Mach number, you can have a subsonic Mach number after the shock. So, this depends only on your mx. So, the moment you have a relation between between the Mach number that exists before the shock and after the shock, I can replace all these my's in terms of mx. So, my px by py can be in terms of my. So, I would rub this. My my is now a function of mx and gamma. Okay. We have in the earlier classes we have derived this function of mx and my and gamma, tx by ty and rho x by rho y, everything in terms of mx and my, which now we can use this to get px by py in terms of mx and gamma, and likewise tx by ty and rho x by rho y, everything in terms of my Mach number before the shock, and get the so called tables which we had seen before. So, in the gas tables for every mx you will have a my and you will have a px by py, tx by ty, rho x by rho y and so on. Okay. So, we can use this tables to do our problems, but before that let us also consider the star Mach number or the m star values before and after your shock. So, I can relate my m square in terms of star values as this, something which we had already seen in the previous class, how to relate my m in terms of m stars. For every m there is a m star that is associated with it. Okay. And we have also seen what is the m star when m tends to infinity. All such things we had seen. The plot looks something like this. So, this is my as m tends to infinity, this is my asymptotic value of m star, which is root of gamma plus 1 by gamma minus 1. So, all those things we had seen. Now, we are going to use this for mx and my and see if my m star x has anything to do with my star. Can I relate my mx star with my star using this relation across a shock? Okay. So, what I do is I take this equation which we had written several times today itself, which is 2 gamma by gamma minus 1 mx square minus 1. Okay. Now, I am going to substitute this particular equation. So, my to this particular equation. So, my value of mx in terms of mx star. So, I substitute instead of my, I substitute this. This would be 2 by gamma plus 1 my star square divided by 1 minus gamma minus 1 gamma plus 1 my star square equals, so I would write it here so that I can write it comfortably. So I would instead of my I would write this. So this would be 2 by gamma plus 1 my star square divided by 1 minus gamma minus 1 by gamma plus 1 my star square equals, instead of mx I again write this 2 by gamma plus 1 mx star square divided by 1 minus gamma minus 1 gamma plus 1 mx square plus 2 by gamma minus 1 all divided by 2 gamma by gamma minus 1. Instead of mx again I write this 2 by gamma plus 1 into mx star square divided by 1 minus gamma minus 1 by plus 1 mx star square whole minus 1. Okay. So, the denominator in this and denominator in this are the same. So, I can cancel out that. So, I can reduce this to 2 gamma minus 1 by gamma plus 1 mx star square plus 2 into 1 plus gamma minus 1 by gamma plus 1 mx star square divided by this quantity 2 gamma into 2 by gamma plus 1 mx star square minus gamma minus 1 into 1 minus gamma minus 1 by gamma plus 1 mx star square. Okay. So, so here gamma plus 1 and gamma plus 1 get cancelled. So, this would be 2 my star square divided by 1 minus gamma minus 1 into my star square. Okay. So, here again gamma minus 1 and gamma minus 1 get cancelled. So, this would be 2 gamma minus 1 mx square plus 2 into gamma plus 1 minus gamma minus 1, gamma cancels and 1 will remain as 2, correct. So, this is a bracket here. So, this will be plus 1, that plus 1 2 mx star square divided by so this is without the denominator. Again the same quantity, it would be 2 into mx star square. So, you can show the final equation is very simple. So, this is so mx there is something wrong somewhere. This cannot be Okay, there is something wrong somewhere. Okay, so the final equation is this. Star is 1. Okay, so if I do the algebra little more carefully, I should get this relation, which is called your Prandtl's relation. Okay. So this just talks about you have a shock, I have an mx, I have an my. Associated with this, I have an mx star, I have an mx my star. The product of this is this. Okay, which also leads to we so my mx star is nothing but Vx by V star, and My star is nothing but Vy A star, because your Tx star and Ty star is the same quantity that we had seen in the last class, because your stagnation temperature does not change. T0x equals T0y implies your Tx star equals Ty star implies Ax star equals Ay star. Okay. Now the product of this is what we had seen just now, which means My star equals 1. So Vx into Vy by Ax square is 1. Or if I multiply the velocity before and after the shock, I should get this. So now I have Vx equals Vy equals Ax star square, which is nothing but gamma r T star. Okay. Now you also know T stagnation by T star equals gamma plus 1 by 2. So I can rewrite this equation Vx into Vy as gamma r T0 into 2 divided by T star. Divided by gamma minus gamma plus 1. So I have replaced T star with this value 2 into T0 by gamma plus 1. So this is Vx into Vy is some constant 2 gamma r by gamma plus 1 into T0. Okay. So the product of this velocity is now just a function of your stagnation temperature. Okay. So or if you see this as your total enthalpy change, then your V square, which is also the kinetic energy. Now this is something that is kinetic energy is lost here during the isentropic during the irreversible process of shock. So the product of those velocity depends only on your stagnation temperature. Okay. And the fluid, of course, gamma and r. So, these are the other important relations which that is coming associated with your Prandtl's equation, m star mx star plus my star equals 1.